Welcome to Westpak's Reliability webinar covering mechanical and environmental testing for a Rackmount network switch. I'm Greg Swinghammer. I'll be your webinar organizer and moderator today. Before we get started, let's take a moment to make sure that everyone is ready and familiar with the webinar control panel. First, you should have a control panel on the right side of your screen. You may minimize this panel by clicking on the orange arrow button in the upper left-hand corner. You can expand the panel by clicking on the same button. Secondly, you have the ability to submit questions using the chat pane located near the bottom of the control panel. We will be answering a few questions during the webinar. However, if we are unable to get to all of the questions during the webinar, one of our presenters will follow up with you. Today's webinar and slide deck will be available on Westpak's website tomorrow. With that, let's get started. Today's presenters are Herb Schueneman and Mike Brown. Mike is a certified reliability engineer, certified packaging professional, and holds an MBA from Santa Clara University. He has been with Westpak for 7 years. Herb is Westpak's president and CEO, and a past lecturer at nearby San Jose State University. Herb, you're our first presenter. Take it away.
Thanks, Greg. We'd like to welcome everybody to the webinar, and first of all, let you know the material that we intend to cover. We're going to go over the background of why we test. We're going to go over product classifications and design of experiments. Next, we're going to be talking about what are commonly referred to as environmental tests. These include temperature and humidity, among others, altitude as well. Broken out of that are mechanical tests, including shock and vibration. And whenever we refer to this, we're talking about mechanical shock, not electrical shock. We're going to delve specifically into the shipping and packaging tests that are often run to duplicate impacts or drops and vibration in the distribution environment. Hopefully we'll have some time for questions at the end. So hang on tight. Here we go. Take it away, Mike.
So, why test? All products will be subjected to hazards throughout their lives. Their shipment, storage extremes, different operating environments, and rough handling and installation. Many products are also subject to regulatory and certification requirements. These often include safety, EMI and EMC compliance, especially for electronic products, and product functionality. Basically, the product does what it is intended to do and is compliant with any industry standards. Lastly, it's a good idea to test to ensure high levels of customer satisfaction and low warranty claims.
I'd like to add here that a question we often hear is, why in the world should we test this product to begin with? Because it's rugged as a tank. And the real answer to that is the product will in fact be tested. That's not the question. The distribution environment and sometimes the in-use environment will see to that. The real question is, who sees the results first, you or your client? For the sake of a quality delivered product, we highly recommend testing the product first so that you can determine if any changes are necessary prior to the customer getting upset with it. Mike, back to you.
Design of experiments, or establishing the test plan. Characterize all the environments or hazards the device under test will see throughout its life. For this webinar, we'll split them into 3 sections: environmental hazards, mechanical hazards, and shipment or packaging hazards. Consider if there are any unique or combined environments that your product may see in its life. Next, determine the acceptance criteria or inspection criteria for your product. It may be acceptable to have some minor cosmetic damage, but it is not acceptable for the product to fail to operate. It's always a good idea to start small. Do basic mechanical or temperature testing early in the process to screen out any major issues with the product. And lastly, consider testing to level versus testing to failure. Testing to level are the minimum hazard tests that the product must survive in order to be brought to market. Testing to failure, or halt testing, is extreme testing in which the product will be forced into a failure mode, and based upon that, product improvements can be made.
I'd like to add that another option that we often see is what's referred to as margin testing, and margin testing does in fact test the product to failure. And the reason for margin testing is a good one from a theoretical standpoint. It tells you how much headspace you have in your design. If you know that a given design has to withstand a certain amount, let's call it vibration or impact or any other of the environmental inputs, then you know what your spec level should be. If you are able to double that with the product, you know that the product has 100% headspace in that particular input. And that is very valuable information for cost reduction, for ruggedization, for eventual package design, and a lot of other things. So there is a case to be made for what's referred to as margin testing rather than just testing to a certain level. Mike, back to you.
Next, not every type of product should be subjected to the same level of test. For today, we'll be talking about a 19-inch rack mount network switch, the 24-point basic network switch. For network hardware, oftentimes they'll be split into three types of categories. Small handheld products, oftentimes those are consumer products. A small product, something that an individual can handle or manipulate by themselves, or a large product that takes 2 or more people to move, a forklift, etc. The environment can either be moderate or severe. A moderate environment might be a general office or a server farm. You know where it's going to go, you know what those operating environments look like. A severe environment means it could go anywhere and can be used in any conceivable location. Because we don't know where this network switch is going to go, we're going to consider all of our tests today to be severe environment tests. So, on to testing. First, environmental testing. The first test we have to discuss is non-operational temperature testing. The first type of test is storage testing. Storage temperatures can range between -40 C and +85 degrees C. These are pretty severe temperature changes, but it's not inconceivable that a product will be subjected to that during its life. Shipping conditions sometimes are tested here. Usually there's a cold condition, -40 C, a tropical condition, 40 degrees C, 90% relative humidity, and a desert condition, which is usually 60 degrees C and either 15 or 30% relative humidity. What I've discussed up to this point are static extreme conditions. Often testing is also done either in a cyclic manner, in which you'll go from between the high and low extreme temperatures at 1 to 2 degrees C per minute, or a shock test, a thermal shock test, where you might transition temperatures between 10 to 50 degrees C per minute. There's a whole slew of test standards that describe this, and the common issues and results are things you would expect. Different thermal expansion coefficients, you have oxidation or corrosion issues caused by humidity, and exceeding material limits, where you get above the thermal limit for a material and you have things melting or getting soft.
I'd like to add that our environmental monitoring has shown conditions in the shipping environment of an extreme in the neighborhood of 70 degrees C, +70 C, in a enclosed truck environment. Now the outside temperature might not be that high, but inside an enclosed structures, you have what is referred to as induced radiation. If you've ever jumped into your car when it's 90 degrees outside, that's parked in the middle of a mall parking lot, it might be 110 degrees inside. That's referred to as induced radiation, and this can cause artificially high temperatures during transit, so don't overlook the high temperatures. Mike, back to you.
For an operational temperature test, usually you're concerned about different components operating above their maximum specification inside the unit. For this test, we have opened up the switch and you can see there's some chip with a heat sink on it. It's been instrumented with thermocouples so we can determine how hot it gets during operation. Sometimes products will have internal temperature sensors that can be used for this instead. A typical operating temperature humidity test will be done at 3 conditions: a cold condition, a warm and wet condition, and a warm and dry condition. The warm and wet condition can be very severe. If any components inside the unit are cool, they may suffer from condensation buildup. The test plan will usually have the unit operating in each condition for somewhere between 12 to 24 hours, and it's also common to try and power cycle the unit on and off to force condensation issues. Common issues and results, as you would expect: electrical problems and components overheating. Here's the data we collected from running our switch to a hypothetical test. 3 conditions were tested: 0 degrees C, 25 degrees C, and 40 degrees C. The red line is the chamber air temperature, and the blue line is the temperature recorded off the heatsink on the unit. You can see that the average temperature rise of the heatsink over the chamber air is about 3 degrees C. This data can be very useful in characterizing a non-operational test. If you know in a 40 degrees C environment, the unit might operate at 43 or 44 degrees C, you could specify a 45 degrees C non-operating test to cover the 40 degrees C operating test. Next up is non-operating altitude testing. These hazards are usually encountered in the shipment or storage environments. Units are usually tested to 14 or 16,000 feet equivalent for shipment testing, or 40,000 feet equivalent if the unit could be placed in an unpressurized aircraft environment. These tests are only applicable for units that have sealed volumes or potted parts. The common tests are only 1 hour in duration and usually are done either at room temperature or at 5 degrees C. Common issues are what you would expect, expanded or imploded parts, but you have to be careful. Oftentimes units may vent pressure only in one direction. So for example, if you go to a low pressure environment and the air can vent out of the unit, and then return to a sea level environment and air cannot vent back into the unit will effectively implode.
I'd like to add that the reason for altitude testing is not necessarily limited to aircraft or shipment, as some might think. All aircraft are pressurized, and the pressurization level generally is controlled, well, it has to be controlled by the pilots. Certainly is controlled by the pilots union, and it's almost always 8,000 feet. An exception is the so-called Dreamliner that Boeing is now flying that is pressurized to a level of 4,000 feet. But almost always the aircraft are going to be pressurized, and 8,000 feet is about the max you're going to get. On rare occasions, so-called feeder aircraft will get to a little higher level, but pilots are required to have supplemental oxygen and pressurization above 13 to 14,000 feet. So there's not a huge upper level there. You actually can experience higher altitude exposure on a truck than you can in the aircraft, because there are truck passages, there are roads that exceed 8,000 feet. There's a passage, for example, in Colorado at 12,000 feet. So don't limit yourself just based on the fact that you never ship by aircraft. You can ship by truck and be exposed to reasonably high levels, certainly in the non-operating environment. Mike, back to you.
Next, we have an operating altitude test. These are usually based upon usage environments. Often this is done at 10,000 feet or occasionally at a 14,000 feet equivalent. The low air pressure greatly reduces the effectiveness of the convective cooling of the product. The common tests are usually longer, between 12 to 24 hours in duration at low pressure. They're usually done at an elevated temperature also of 40 degrees C. The common result we see is the unit overheating during test. Here's the operational altitude data we collected for our sample product. You can see the air temperature is held at a constant 40 degrees C, and the air pressure is started at sea level and then reduced to a 10,000 foot and then 14,000 foot equivalent. The unit starts with a 3 degrees C temperature rise over ambient and ends with a 4 degrees C temperature rise over ambient. If the product were convectively cooled with the fan, this disparity would likely be much greater. Other environmental tests that are less commonly done on a product like a servo switch would be UV light exposure for outdoor weathering, corrosive atmosphere or salt fog testing, and then also either water spray or mechanical ingress testing. All of these are going to depend on the type of product, but are other things to consider. Some final thoughts on environmental testing. Think about typical inputs versus worst case scenarios. While the unit is operating, consider high or low voltage inputs. Always think about safety. Do the thermal cutouts protect the product? And if the device does enter some sort of failure mode, is there a hazard, either electrical or mechanical, to a user? And as I mentioned in the beginning of the presentation, think about your failure criteria. Is cosmetic damage okay? If so, to what level? Does the product need to continue to function in harsh environment, or is it okay for it to shut down? And lastly, Again, is it still safe?
I'd like to add that in our experience, damage criteria or the definition of what constitutes failure is one of the biggest sore points, if you will, or sticking points in the whole test. So you have to be able to understand what constitutes failure or damage to your product. Some people will actually take and make classifications out of damage in terms of moderate, normal, or severe, things like that. Sometimes damage can be considered cosmetic. Sometimes it's non-functionality. We often encourage clients to consider damage as any condition in which you would not want your customer to receive the product. However you define it, it's very important that you understand that this must be defined prior to actual testing.
That wraps up environmental testing. At this point, we'll pause for some questions. Greg, do you have any questions for us?
Thanks, Mike. We don't have any questions right now, but remember, everybody, please feel free to send your questions in, and we'll try to get them answered during the webinar. If not, Mike or Herb will follow up with you after the webinar. Thanks, everybody. Back to you, Mike.
All right, let's keep going. Mechanical testing's next. First, we're going to talk about some basic setup. Oftentimes, during mechanical testing, we'll instrument the product with accelerometers. These can be used to characterize the resonance of the product and to help characterize the response to different mechanical inputs. Also, we can characterize the response to different operating inputs. Those are things like cooling fans, air conditioning in a large industrial environment, hard drive spinning, etc. A typical test setup will have 1 to 5 accelerometers. Usually there's one accelerometer on the chassis of the unit, and there's also 1 to 4 accelerometers on some components of interest.
I'd like to add that accelerometers today are not like they used to be. They're much smaller, more sensitive, generally speaking, and easier to mount. In addition, if some units simply can't hold an accelerometer, there's no way to get to it, you can use a laser vibrometer or a similar type of instrument that is non-contact. Also remember that most traditional accelerometers have a cable. They're not wireless yet. Hopefully they will be in the future. But right now you have to be able to route cables to and from that transducer. And occasionally that winds up being the worst of the problems. But Mike is right. We have to be able to monitor the results. And right now the best option for doing that is with accelerometers mounted on critical components. Mike, back to you.
So first we need to determine where to mount our chassis accelerometer. One way to do this is to tap the exterior of the unit to hear the highest pitched or most rigid location on it. Usually you can identify it visually as well, looking for places where there are several screws. You can see I've now determined where to put the accelerometer near the AC power inlet. Next we'll mount the accelerometer. Squirt a little bit of glue onto the area where the accelerometer is to be adhered, press it on, and wait 15 to 30 seconds for the glue to dry. It is also common to monitor components or internal parts of the product. In this case, we're going to be concerned with the PCB backplane or the big green board. The red circles show where there are mounting screws holding the backplane to the chassis. The maximum deflection on the board will be experienced in the largest free span, or right in the middle of it. It's not practical to mount there due to the traces being close to the surface, so I'm going to mount the accelerometer just above the center of the backplane. You can see it circled in red. I put a piece of Kapton tape down to help prevent any damage to the PC board. Here's a picture with the accelerometer mounted to the unit. You can see it's just hot melt glued onto the tape.
The whole area of mounting of a transducer to a test specimen is one that's evolved over the years. Many of you may be aware that many transducers come with beeswax attached to them. So in times past, that mounting technique has been considered to be acceptable. Some people insist on using super glues or some fast-acting epoxy glues or things like that. Some insist on mechanical mounts, such as the military. Okay. We make wide use of hot melt adhesive because of its wide acceptability for various types of accelerometers and mounting conditions. However you do your mounting of accelerometers, make sure you convince yourself that you're not severely altering the signal, that you get the kind of bandwidth through that mounting technique that you're looking for, and that you're satisfied with the ability of the transducer to hold in place and give you the data that you're looking for. Again, a wide variety exists. You simply have to be comfortable with the technique that you're using. Mike?
Of course, not every product was designed with accelerometer testing in mind. In this case, I had to snip off some of the airflow grill in order to allow the accelerometer to get into the unit. This is very commonly done. The last part of setup is the unit orientation. You can see in blue tape on the left side of the unit, I've written some numbers and letters. First, we have the axes, X, Y, and Z. Z is usually vertical up, down, X is left to right, and Y is front to back. The numbers are the faces, and this will correlate with the package testing we'll conduct later. The top is 1, the right is 2, the bottom is 3, the left is 4, the front is 5, and the back is 6. By clearly labeling a product and taking lots of pictures during testing, you always have a much better idea and record of what you did for your test report.
We'd like to remind everybody that it's important to identify the orientation of the product before you actually put the transducers on. After you have it all assembled, you certainly want to be able to make sure that the signal that you're getting is from the axis that you intend. So with your X, Y, and Z axes and plus and minus direction all identified, make sure that your accelerometers are applied the same way. And this is especially true if you happen to be using a triaxial accelerometer, one that will measure 3 axes at the same time. So one of the reasons for this is to save time and money. You don't want to spend your time opening up the unit and reorienting the accelerometer 2 or 3 times to get it right. So remember to orient the product and the transducers before you close it up. Mike, back to you.
Our first mechanical test is sine vibration, both operating and non-operating. There's a whole bunch of reasons to conduct this test. For non-operating, the primary purpose is usually a resonance search, trying to identify where different components of the product resonate. For the operating test, usually this is only applicable to unique and/or severe end-use environments. Sometimes it's used as a general mechanical stress test as well. The typical test will be conducted in all 3 axes sequentially. For resonance search, usually we're only interested in 2 sweeps, one up and one down through the frequency domain. The stress test can be more severe, usually 10 sweeps, sometimes incorporating resonant dwells depending on the response of the product. The acceleration levels are usually 0.1 Gs to 5 Gs constant acceleration. Sometimes it's truncated at the low frequency due to the limitations of test equipment, and a frequency domain for this type of product is typically 5 to 500 Hz. Common issues: during an operational test, it's not uncommon to see things intermittently shut down or have operating errors, especially when they go into mechanical resonance. And for the general stress test, sometimes unsupported components or surface mount components will come off, or just other general mechanical failures can occur. Here's a sine vibration control plot. This was a half G constant acceleration sweep from 5 to 500 Hz. The profile and control lines are right on top of each other. The table effectively ran perfectly. This is the response observed on the unit's chassis accelerometer. The left-hand side is a unitless ratio of response compared to the control input. You can see that the chassis response is effectively flat throughout the entire frequency domain. This means that the resonant frequency of the chassis is likely above the range that was tested. The PCB backplane, however, is a different story. You can see here that in the 200 Hertz range, there were clear resonant peaks. The two recorded were at 171 Hertz and 216 Hertz, with an amplification of 25 times the input. What this means is if the unit were ever subjected to high frequency vibration, it could literally shake itself apart. So design considerations should be made to help prevent the unit from ever being exposed to that high level of high frequency vibration.
I'd like to add a comment here about sine vibration in general. It's an excellent diagnostic tool. It's been around for a long time. It's probably the oldest vibration diagnostic tool we have. But it occurs in one place in the world only, and that's in the laboratory. It is not a real-world test at all. So all we're trying to do here is really excite the product, and we excite it sinusoidally. And one of the reasons we do that is to find out the exact natural frequency, natural or resonant frequencies of the components inside the product. But you have to understand that when you're exciting a product at a single frequency at a time, which is what's happening here, there's no such thing as destructive interference in the amplitude measurement, and therefore the amplitude levels that you get in sinusoidal vibration, which is that deviation from the in the vertical axis, is artificial. It's normally much higher than you get with a random vibration excitation, because there you're exciting all frequencies simultaneously, and you have constructive and destructive interferences working for you. But in sine vibration, that's not the case. So the advantage of sine vibration is very clean. You get a good, clear indication of the natural frequencies, but the amplitudes are not accurate. And make sure, well, and that's not a true statement. Certainly they're accurate, but they're not realistic. Okay, because sine vibration, again, occurs in one place in the world only, and that's in the laboratory. Mike, back to you.
The next we have random vibration testing. This is also commonly done both operational and non-operational. The non-operating test requirement is pretty clear. All units will be subjected to some level of vibration during shipment. The operational test should be based upon the end-use environment the product may go. Like sine testing, all tests are usually conducted in all three axes. The test duration is somewhere between 10 to 60 minutes per axis. Non-operating tests are usually more severe, at up to 5 GRMS. Operating tests are usually less severe. Common issues, much like sine vibe, are operational issues and components coming apart. Here we have a video of a non-operating random vibration test. This one is 1.35 GRMS with a frequency range between 2 to 500 Hertz. If the video file isn't working for you, we'll have it posted on our website tomorrow. Here's the PSD, or Power Spectral Density Control plot for the vibration test. You can see this one goes from 2 Hertz to 500 Hertz and is shaped to have a maximum vibration input between 10 to 100 Hertz. Like the sine test, we've captured the response data. You can see the chassis, as with sine, basically has no response in this frequency domain. The PCB, however, does have a significant resonant response. Like the sine test, the resonant response frequencies were 170 and 216 Hertz, with amplification levels of up to 20 times the input. If tested for a long period of time, it's possible that this test could cause mechanical issues.
It's important to note, I think, that this data is real live data, and it shows what actually happens from both a theoretical and an actual standpoint. Namely, that this spring mass system, or it's actually multiple spring mass systems that we're measuring, respond the same to sinusoidal and random vibration. And that's key. All spring mass systems will respond at their natural frequency regardless of the excitation, simply because they can't do anything else. That's an important concept to remember. So that's one of the reasons why both sinusoidal and random vibration are still used, that they both give you approximately the same results. It should also be noted that to do a sine test, you have to sweep through the entire frequency band of interest, one frequency at a time, depending on the sweep rate. Okay, so it can take a while to do that. Random vibration, you're exciting all frequencies and all amplitudes simultaneously, so it can be a shorter test if all you're looking for is the natural resonant frequencies. If you're looking to do a fatigue test, sinusoidal may be a better test because then you can dwell at the natural frequency and get some good severe input. So various tests can be done. It all depends on what you're looking for. Mike?
Our last mechanical test is operational mechanical shock. A typical test will be a half-sine pulse with a duration between half to 18 milliseconds. Shorter duration pulses simulate bare product events, like a product being dropped a few inches onto a table. Longer duration shocks simulate what a product may see during shipping. Peak G levels depend on the product. They're typically between 6 to 50 Gs. Units will usually be tested in all 6 orientations, X, Y, and Z in both directions. Results are usually mechanical in nature. Here we have a non-operational mechanical shock test. Typical test is very similar to an operational test, just conducted to a higher level of severity. Sometimes a trapezoidal pull shape is used, which Herb will talk about in a second.
Should be noted during the shock testing, especially in the non-operating mode, that the product will respond differently to the shape of a waveform that it sees. And that waveform can be shaped by a number of things, typically by the cushion that it's in, and if it's in a packaged environment, or the surface that it's dropped onto, if that happens to be the source of the shock. And that's one of the reasons why a trapezoidal waveform is highly recommended for this. And that is that the response spectrum of a product, any spring RAS system, to a trapezoidal pulse is the most severe of any waveform possible. More severe than a half sine, more severe than a sawtooth pulse or any other waveform. So it's highly recommended to use the trapezoidal wave for this. It's not very common because a lot of people are hung up on using a half sine. They're easier to program, they think. Although trapezoidal pulse are incredibly easy to program. If you have a constant pressure cylinder, all you have to do is add nitrogen gas or change the drop height to change the pulse. It's easy to do. It's just not often done. Those of you familiar with damage boundary testing or product fragility analysis for shipping recognize that it is called out in standards such as ASTM D3332. But for typical environmental testing or mechanical shock testing of products, often half sine is used simply because it's easier. But you have to recognize that a product may pass a 50G half sine but fail a 50G trapezoidal pulse, and you have no control over the pulse in the real environment. So it's highly recommended to use the most severe shock, and it will result in the best possible data in that it is conservative. That is, if you pass a 50G trapezoidal pulse, you'll pass a 50G pulse of any way, shape, any time, any place. So that's why it's highly recommended. Mike, can you continue from there?
Here we have a video of a shock test being run on an electric shaker. This is a 40G 11 millisecond half sine shock pulse. Here we go. One big shock in the middle. Play it one more time for you. Right there. Here's the data from the shock test. So you can see the green profile, the ideal waveform, and over it a blue line which represents what was actually done. The table controlled this one very well. The chassis reacted just the same way the table did. It was rigidly coupled. Here's the data from the PCB board. You can see that it didn't respond like the chassis or table input. Basically, at the center of the board where we measured it, it did not have a significant mechanical response to the test input.
Mike has shown you a typical half-sine shock pulse with a duration of 11 milliseconds and a peak acceleration of 40 Gs. The 11 millisecond duration is very common. You find it in a lot of different environmental test specifications, but it's not very significant. It was has its origin back in the 60s with shock testing that was originally done on what was referred to as the Berry sand dropper. And it just happened to be a noisy machine that dropped a shock table into a bed of sand. And 11 milliseconds was about the best people could make out of it. So it kind of became a standard, and it kind of a life of its own, and you see it around everywhere. But it's important to recognize that there's no particular significance to 11 millisecond duration. It just happens to be a good medium kind of forward, if you will, type of waveform. So don't get too concerned about adding or not adding an 11 millisecond shock pulse to your environmental test standard. Remember that they came about because of kind of a grandfathered thing way in the past, and has just kind of moved forward in time. Again, nothing special about it. Mike?
Next is manual handling. Usually this test is conducted to simulate low-level drops, something that you might see during installation. Here we have a 3-inch drop. The wood block is placed under the unit and then pulled out, and the unit's allowed to freefall drop. Usually this kind of testing is conducted on all faces or sides that might be subjected to a drop test. Our last mechanical test is mechanical cycling, basically evaluating all the components that might move inside the unit. For our network switch, that means the AC cord plug on the back and all the LAN connections on the front. For a product like this that'll likely be installed and left to sit, 100 cycles might be a good number to use. If you can, try to define the cycle force, speed, and duration. Units like this could be tested by hand or by machine. With 100 cycles for one unit, it's likely to be way more economical to do it by hand. Test standards are difficult for these. Usually they're specified by the company conducting the testing. Common issues are exactly what you would expect: quick wear out, things breaking, or changes in actuation or insertion removal force. This wraps up all the mechanical testing. Let's pause for questions again. Greg?
Thanks, Mike. We got some questions here. The first one is, should both sine and random vibration tests be performed during qualification reliability testing every time? What is the advantage, if any, of one over the other? Which one of you guys wants to take that one?
Well, I'll start. The short answer is yes, it's a good idea if you have the time and resource to conduct both tests, because they're going to tell you slightly different things. The Sine test very cleanly shows you all the resonant points of the product, the inside parts of the product, but the random vibration test is going to be generally more representative to what you would see in the field, both in shipment and in operation. So if you can, try and do both.
Let me jump in here and add that a good way to answer that question is to say, what the heck is the difference between the two? In sinusoidal vibration, you're essentially exciting a spring mass system or multiple spring mass systems at one frequency at a time. So that's one input, one response, or maybe multiple responses, but one input, that's the critical thing. So what happens when you put in a single input? Well, the thing is going to respond in a singular way. So if there are harmonics, you're not going to excite those. If there are subharmonics, you're not going to excite those. If there are constructive and or destructive interferences between waveforms in the systems, you're not going to excite those. Okay, but you will excite that one frequency at a time. So you're going to be able to see exactly what the response of the unit is to that one frequency only. Random vibration is basically all frequencies and multiple amplitudes at the same time. So it's going to be more realistic in terms of how that spring mass system, called your product, will react in the real environment, because that's what it sees. It never sees sinusoidal vibration. That's only a diagnostic tool. What it will see is random vibration at some level. Now, it might be pseudo-random, that could very well be, but it will certainly not be sinusoidal. So when you excite a product with a random vibration signal, you will in fact excite and you'll see the effects of constructive and destructive interferences between components at the same time. And that's exactly what's going to happen during the product's life cycle and or distribution. So of the two, if you had to do one or the other, my recommendation would be obviously random. If you can afford to do both, as Mike said, why not? It certainly was going to give you a little more information, a little more insight, and that's never a bad thing. Greg, any more questions?
We do. I'm going to try and lump them all into one. Could you go into a little bit more detail in what you mean by natural frequency and what is the importance of knowing that natural frequency?
Let me take a stab at that first. The natural frequency, or what we often call the resonant frequency, is where any spring mass system wants to respond. I'll give you a good example. If you whack a bell, it's always going to sing the same note, the same tune, because that's all it can do. And it happens to be at an audio frequency where we can hear it. However, any spring mass system is going to respond the same way. When it's excited, it will respond at its natural frequency. It doesn't respond at the frequency that it's excited at. It responds at its natural frequency or resonant frequency, and that's why it's called that. So in the sinusoidal and or random vibration test, we go through all these frequency bands, if you will, and we measure the response, and we see where that component wants to respond. In the examples that we showed earlier, we saw what it was 176 hertz and then 216, something like that. Those are the natural frequencies of those components. That's where they want to respond, and that's where they always will respond. I always told my students in class, all spring mass systems respond at their natural frequency because they can't do anything else. I think I told them that the first day of class, and I told them it would be on the final, and it was. And they all got it right. So just remember that. All spring mass systems respond at their natural or resonant frequency. You can excite them differently. They're gonna get excited by different means and modes and everything else, but they will always respond at their natural frequencies. Greg?
Kind of a follow-up on that. Why is it important to know the resonant frequency of your products?
Perfect. I was going to jump in on that. This is important because if you have an input of, say, 1 on our data, the response was 20 times that at its natural frequency. So think about that both from an acceleration standpoint or from a physical displacement standpoint. That can be extremely significant. So if your product is in the field, at least this one, and there's some vibration input in 150 to 200 hertz range, the product could very easily shake itself apart. The response of the PC board in a product anyway is 20 times the input, and that's why this is an important test to run. So both in your transport packaging, which we're going to talk about next, and in your natural use environment, if you expect to see vibration hazards like that, either you can adjust the design of the product or the design of the package to make it less susceptible to those hazards.
Herb?
We know from the product testing that structural failure of any product is unlikely at the vibration levels typical of either in use or the distribution environment. But as Mike said, it's only when those systems are excited at their natural frequency, when they have these very high responses. We've seen 50 to 100 times the input on very undamped systems. At that level, suppose you're exciting it at a quarter of a G and its response is 100 times the input at its resonance. That's 25 Gs. Things can easily fail, fatigue, lots of other things can happen. So the natural frequency is very important to us because that's where failure is most likely to occur. Okay?
Cool. Thanks, guys. It looks like we don't have any more questions at this time, but please send them in. We'll try and get some more questions in at the end. If not, Herb or Mike will follow up with you after the webinar. Back to you guys.
All right, for the third half of our webinar, we'll talk about shipment or packaging testing. Every product will be shipped. Common test inputs include environmental conditioning, chamber testing, product freefall drop or side impact testing, compression, vehicle vibration, and some other hazards. Common standards are either from ISTA or ASTM. The most common one for small parcel with a pretty quick and easy test plan is the ISTA 2A standard.
These test standards for packaging have evolved over the years. The ISTA 2A used to be for international shipment, and they refer to this as kind of a general simulation, which basically means it's not designed to duplicate any particular type of environment, but what would generally happen when you ship the product. So these what we refer to as a package integrity test are designed basically to bring the hazards of the distribution environment into the laboratory and then subject the product package system to these hazards and then simply evaluate the results by most of the time visual evaluation, sometimes by actual monitoring. But the general term for these are package integrity tests. ISTA, the International Safe Transit Association, is a big producer of these kind of procedures. ASTM, American Society for Testing Materials, is another one with their D4169 and 7386 procedures, things like that. Number of other procedures as well. So all these are designed to basically say in the laboratory whether or not successful shipment of this product is likely. Mike?
For this, earlier we talked about product orientations. You can see I've transferred the product orientations to the package. So this way you know how the product is sitting inside the package during all the packaging testing. The environmental conditioning is meant to simulate the different extreme environments the unit may see during shipping. This both subjects the unit and its package system to the harsh environments. Usually this causes issues with the packaging, the corrugated fiberboard or cardboard getting damaged by the moisture content in the air. Sometimes there's condensation on the EUT, sometimes tape or closures come open.
It's important to note that, as Mike stated, the environmental conditioning is conducted on these materials and package systems prior to the mechanical test because they will absorb moisture, and it's possible to have a product package system pass a test with a dry container and fail the same test with a moisture-laden one from high humidity conditions. So make sure that you determine your conditions correctly and conduct the test procedures in the sequence indicated, which is almost always environmental conditioning prior to the mechanical test. Mike?
The first major mechanical test is a Freefall package drop. The ISTA 2A test calls out 10 drops, 1 on a corner, the 3 radiating edges, and all 6 faces. The drop heights are based upon the weight of the product. In this case, the product being under 20 pounds, it would be dropped from 38 inches. Common issues are the box denting or the box coming apart, and in turn, the product being damaged on the inside. Here we have a video of the Freefall drop test. You can see the drop tester dropping the box and the capture system on the left recording the accelerometer data. Let's look at the data. So for this, the box is not designed for transport packaging on its own. It would probably be shipped in a case, or it would be overpacked if it were to be shipped by itself. The chassis in the Z-axis, the direction we dropped it, saw a peak G response of 250 Gs. Typically for these types of products, you may not want to allow a peak G of greater than 50 or 100 Gs. This all closes the loop on this webinar in that if you know what the fragility of the product is based upon your earlier testing, you know if the results of this testing are acceptable or not. The PCB is a similar story, but even worse. It saw a peak G of 420 Gs. That's very severe. So if this were your shipment packaging, it probably should be redesigned to better protect the product. Next is package compression. This is used to simulate a top load the package might see on a truck or on an aircraft. The basic concept of this is to think about how much free space there is vertically above the unit, figure out what the mixed density of the cargo might be above that, usually 10 to 12 pounds per cubic foot, and to try subjecting the box to that load. The formula here is the weight of this unit, which is 3.7 pounds, times how many there might be in a stack on a 90-inch stack, minus the one on the bottom, a safety factor of 4, and they also have another factor of 1.4 to account for the apply and release nature of the test. Anyway, for this box and this test standard, it needs to withstand a top load of 415 pounds, which it did. Common issues and results would be the box failure or the internal components being damaged as they're supporting the load instead of the box.
Many of our clients question the suitability or even feasibility of conducting a compression test on the product package system. But remember that what are you really buying with a package? Well, you're buying the protection from the environment, and you are buying the ability to stack this up. And even though you may not stack it up in your facility, I guarantee you that when you ship it, it's going to get stacked, unless it goes all the way to the roof. cube utilization and shipping equals good logistics, and that's exactly what the distribution folks want. So your product will be stacked, it will be compressed, and it's a good thing to test for that ahead of time. It's a relatively easy thing to correct. If you happen to have a low compression value, you can add strength by a different design of corrugated box, for example. So you have a lot of flexibility here, but without the data, you just don't know if you have a problem. Mike, back to you.
The last major mechanical test for packaging is vehicle vibration. This simulates truck or aircraft shipment. The ISTA-2A test requires 30 minutes on the base of the unit, 10 on the top, side, and end. That whole sequence is conducted twice. Common issues results are problems with the unit, and then also problems with scuffing on the exterior of the packaging. Here's a video of vehicle vibration running. The best way to think about this is a truck going down the road, but all the smooth parts of the road are removed from the profile. You just have the major mechanical events. The data looks like this. This is the control profile. You can see the frequency domain on the x-axis and intensity on the y. The shaped profile is based upon an aggregate of collected field data for truck and aircraft shipment. Inside the package, the chassis does have a mechanical response. You can see the peak response is at about 15.5 Hertz with an amplitude of 2.5 times the input. You can see that relatively low response is good. You generally want to be under 5 to 10 times the input. So from a vibration standpoint, this package is looking good. Here's the response for the PCB. You can see the chassis response shown here at about 18 Hertz, and you can also see the PCB's own resonant response at about 173 Hertz. As you may recall, it resonated there during our bare product sine and random vibration tests. Some parting thoughts. Start by defining the environment and any regulatory requirements your product may need to meet. Establish the acceptance criteria for your product. Think about all the design and material choices first before you test. If you can, try to reference existing solutions. Always start with the smallest portions of your test plan first, and test as early as possible during your design and prototyping process. Take all the corrective actions possible before you finalize your tooling. And lastly, don't ever forget you have to ship it. We'll pause for questions at the end. Next, Greg's going to cover some upcoming webinars that Westpak's offering.
Thanks, Mike and Herb, for that fine presentation. Our next webinar will be the fourth in our Packaging Dynamics series. You can check our website under the Resources Webinar tab for more information. You can also register for the webinar or wait for your personal invitation to arrive in your inbox. We do have one more question. Is ISTA 1A still considered a valid test?
Let me try to tackle that one. Good question. It all depends on what you mean by a valid test. It's been around for a long time. I think that basic sequence was developed in the 1930s. And it's been around. It consists of a series of 10 freefall impacts and then an hour of vibration that can be either a repetitive bounce test or a random vibration test. So is it valid? The ISTA organization, International Safe Transit Association, that's what it stands for, calls it a general simulation. So they're not claiming that this procedure duplicates any particular environment, and I think that's a valid and correct call. It probably doesn't. But what it does do is it provides some general excitation for the product. It's kind of the difference between a stimulation and a simulation. So they're saying that it doesn't simulate anything. It does stimulate the product package system so that you can see what its responses are. So in that context, yeah, it's a valid test. It can certainly tell you something about the product. Is it a valid simulation of the distribution environment? The answer is probably no. It's probably not, and they admit that. Interestingly enough, people who have done a lot of testing or people who are very interested in this, let's take one particular example. The folks who ship a lot of package systems, the FedExes and UPSs of the world. Generally what they tell us is that any package system, any product package system that has been subjected to even a minimal test procedure and pass it will have a very high percentage of successful shipment through their systems. They generally say that's not a problem. Where they have a problem was with product package systems that have not been tested. Then that's when damage is more likely to occur. So the exact procedure is not as important as whether or not you run any procedure at all, at least according to these people. We would further add to that if you're going to test at all, you might as well use a valid test procedure, one that has been shown to properly simulate a given environment, and why not? If you're going to spend the money to do it right. And so that would be our response to it. But if you're concerned that it is ISTA 1A a valid test procedure, the answer is obviously yes and no. I hope that answers the question. If there's any more, that's actually pretty ambiguous now that I think about it. But anyway, if there's any more clarification that's necessary, just give us a buzz on the format that Greg indicated, and we'll try to further define or answer the question. Greg, back to you.
Thanks, Herb. Great segue into the next slide. So we have two locations, one in San Jose, California, and another lab down in San Diego, California. And here's the contact information for both of them. Feel free to give us a call or send us an email anytime you like with any questions, concerns, or we can help you work through what test to choose for your testing needs. If you missed anything or would like to listen to the webinar again, please go to our website at www.westpak.com under the Resources and Webinar tab. The webinar materials should be uploaded by Monday. We will be sending you a short survey within the hour. Please fill it out as we highly value your opinion regarding today's webinar. You will also have the opportunity to ask questions and suggest new webinar topics, as we're always looking for new things to talk about. Thanks for attending. I'm Greg Swinghammer. Make it a great day.